Non-equilibrium molecular dynamics, or NEMD in short, is a commonly used tool to study phenomena like friction and wear in tribochemical systems. In today's video, I want to show how to set up an NEMD simulation to calculate the friction coefficient of two sliding quartz surfaces with the reactive force field ReXFF. The structure consists of two slabs placed on top of each other. The slab on the top is going to be sliding over the slab at the bottom. To control the external forces applied during the NEMD, we have assigned different regions here. The sliding and bottom slab are two separate regions labeled A and B. Further, the silicon atoms in the bottom layer of the stationary slab are assigned to a separate region called fix, so we can later lock them in position. And finally, all atoms other than the fixed ones are assigned to a region called free, so they can all be thermostated to 300 Kelvin. To set up the external forces and velocity, change to the NEMD panel in the GUI. Here you can now select the previously defined regions from a drop-down menu. For this demonstration, we shall go with the velocity of 0.0005 angstrom per femtoseconds or 50 meters per second and a normal force of 10 nanonewton. These forces will now be applied to all atoms in that particular region, and they will be excluded from any thermostating. In the MD trajectory options panel, we select right engine gradients, as we need the gradients for the calculation of the friction coefficients later on. Now we only need to request some standard MD settings, such as time steps, thermostat and so on, but in lieu of time, we skip that and start the calculation. You can find the complete input file in the YouTube video description if you're interested in the details. Once the calculation is done, we can open the trajectory in AMS movie. Here we can visualize the normal and the friction force. You can see that the Z force is around the requested value of 10 nanonewton, while the friction force oscillates in cycles around 12 picoseconds, so one needs to average over such a cycle to get reasonable friction coefficients. To calculate the friction coefficient, we use a small script that you can find in your AMS home directory. If you don't know how to run scripts with AMS, have a look at the video description for a link to the according documentation. By passing the block variable, I request an averaging of forces every 12 picoseconds, so roughly the frequency in the force fluctuation we saw earlier. Now I can average the forces and use the average to calculate the friction coefficient. So that's it for today. I hope you found this useful, and as always, we're happy to answer any questions or comments below this video.